Which function has a local minimum with a value of 1? Has a local minimum with a value of 1. So let's think about this a little bit. So they tell us the x values, and we see x increasing from -4 all the way to +4. So our x values are increasing, and they give us different functions here. And they essentially say which of these functions have a local minimum value where the value of the minimum is 1. So they hit a minimum point at 1. So that means that the value of the function must be 1 at that minimum point. So let's see, we can see candidate points right over here. F of x hits 1 right over there. G of x hits 1 right over there. And h of x hits 1 right over there. And let's see, that's the only time that they hit 1. Now let's think about which of these are minimum values. So on f of x, when we go from -2 to -1, we are increasing from 0 to 1, and then we increase again. Well, that's not going to be a minimum value. We are increasing. So let me draw a little axis right over here. So let me actually draw the whole thing just to make it clear what we're doing. So we have -4, 3, 2, 1, +1, 2, 3, 4, and of course this is 0. -4, -3, -2, -1, 1, 2, 3, 4, and this is going to be 0 right over here. And we're going to care about what's happening when these functions hit 1. So f of x, when x is equal to -2, is 0. When x is equal to -1 is 1. And then when x is equal to 0 is 5. So 2, 3, 4, 5 is that right over there. And if we assume that these are sampling from the function, we actually necessarily can't make that assumption here. But if we assume that these are sampling, then if this was a continuous function, then we would assume that the function does something like this. And so it's clearly not a minimum point right over here. We're increasing into negative, or increasing into 1. So this is not a minimum point. Now let's look at g of x. Let's see, when g of x is 1, we're at 2. When g of x is 1, we're at 2. When g of x is at 2, we're at 1. And when g of x is 3, we're at -1. So we are at -1. So this is the opposite. We do decrease into that value when the function hits 1, but then we keep decreasing. In order for this to be a minimum point, we would have to decrease into it and then increase out of it. So this right over here is also not a minimum point. Now let's look at h of x. When x is -4, we're at 5. When x is at -3, we are at 1. And when x is at -2, we jump back up to 3. So this looks like a minimum point. We decreased going into it, and then we increased going out of it. So this is our local minimum point. And if this was a continuous function, it maybe might look something like that. So we will go with h of x.